Today I'll be talking to you about some recent work that we have done, which has recently been published, and here's the link here. And it's about how we might utilize quantum walks in the LHZ embedding. And so, first a bit about what the problem that we're trying to solve. And as people that like solving problems with continuous time quantum computing, we like to solve optimization problems. And these come in a variety of styles, but as physicists, we like to represent our optimization problems on Ising models. Specifically, we like to encode the solution to our optimization problem in the ground state of an Ising model. And something interesting about these optimization problems encoding onto Ising models is that they tend to have quite high connectivity. And this might cause issues when we talk to our experimental friends, and on the hardware, they actually have something with much lower connectivity. So how do we get around this problem? So one way to get around this problem is to use an embedding. And there's a few options that you might be able to use. So for example, if you're using something like the D-Wave machines, you might use minor embedding. Another option would be to use some kind of gadget in order to embed your optimization problem. But what I'm going to talk about today is something which I would describe as long-range to local embedding, and specifically one called the LHZ embedding, which was first introduced in this paper here. And so, yes, once we've selected the embedding that we would like to use in order to have our optimization problem, we then need to use a form of quantum computing in order to find its ground state. And the type of quantum computing that I'm going to talk to you today about is quantum walks. And we'll use this to find the solution to our optimization problem. And so a brief overview of what I'll talk to you today in my talk is first off, what exactly are quantum walks, and then how we can use these quantum walks within the LHZ embedding, and then how we might utilize the LHZ embedding in order to improve the performance of our quantum walks, and finally the summary and conclusions of our work. So, first things first, what exactly are quantum walks? Well, a quantum walk is simply the quantum analog of a classical random walk. And in a classical random walk, we start off with our walker. They start on an initial node, and they have a choice of 3 edges to pass along to get to the next node. And they choose this randomly. On the other hand, in a quantum random walk, we have our quantum walker. It also has 3 possible choices of edges to move along. But instead of having to make this choice, classically we can use this, we have a superposition of the 3 possible choices that the walker can walk to. And you may have noticed that I have labeled these nodes with the initial one with 0, 0, 0, and then 1, 0, 0, 0, 1, 0, and 0, 0, 1. And this is because this walking along an edge is equivalent to flipping a bit. And we can represent this with a sum over the Pauli X matrices. And if you're into your continuous time quantum computing, you may recognize this term because you may have seen it before in the Hamiltonian for adiabatic quantum computation. And if we compare the Hamiltonian of adiabatic quantum computation to that of a quantum walk, we can see that they are actually very similar. We both have our initial Hamiltonian and our problem Hamiltonian in both cases. The difference being that in an adiabatic quantum computation, we have this S here, this schedule term, which starts off at 0 and then slowly varies towards 1, so that we end up in the ground state of our problem Hamiltonian. On the other hand, for the quantum walk, we have this time-independent term gamma here, which instead of varying, we set at a specific point, which will optimize the success probability of our quantum walk. And how do we compute using a quantum walk versus adiabatic quantum computation? So if we look at both of our Hamiltonians, similarly, we start off in an initial state and we evolve over time to find our final state. And for adiabatic quantum computation, we see that over time the success probability slowly rises towards 1. However, on the other hand, for quantum walks, we see that we get oscillations between 0 and a certain value. And what we don't want to do is, for example, when we measure our final state, accidentally measure here where we have a low success probability. So instead of just measuring at a final time t, we take an average over time, which we call the finite time success probability. And if we were to measure this finite success time probability versus this gamma parameter here, we get a plot which looks like this. And we see that at some value of gamma here, the finite time success probability is maximized. And we call this value the optimal gamma, which we want to set for our quantum walk Hamiltonian. And as we're using this toy problem here, this value of gamma optimal can be found analytically. However, this is just a toy problem. By setting this mark state with a lower energy, we, by definition, already know the answer. So how does this look when we replace it with something a bit more realistic, such as an Ising model? So instead of our mark state problem, we now have an Ising model problem, which we would like to find the ground state of. We repeat the same evolution over time with our quantum walk Hamiltonian, finding the finite time success probability, and then we plot this again versus this gamma parameter, and we see similarly to the toy problem, we again have this behavior where we have a peak in our success probability at this value of optimal gamma. However, differently to the toy problem, this value of optimal gamma can no longer be found analytically or efficiently. So what do? Well, we can approximate this value of optimal gamma using a heuristic, which was first introduced in this paper here. And I won't go into the details here, but this technique involves maximizing a parameter, gamma, which relies on the gaps between the energy levels in our problem Hamiltonian. And as you can see, it doesn't quite match the true optimal gamma, but we can still have some improvement in our success probability by using this parameter. So how does using the LHZ embedding affect the performance of the quantum walk? So before I go into how it affects things, I thought I'd quickly recap what the LHZ embedding is. If you hear Roland's talk earlier, then you'll seen this before, but I'll do a brief recap. So we start off with our Ising model Hamiltonian, with its high connectivity and long-range interactions. And the idea behind this is the LHZ embedding is that we want to remove these long-range interactions so that the qubits are locally locally distributed and no longer have these long-range interactions. So what do? We start off by mapping the couplings within our Ising model so that they become qubits. And we represent the parity, so the LHZ embedding is also known as the parity embedding, the parity between the qubits in the original model so that they are represented in the LHZ model. So for example, the spins are two different spins, we represent this with a 1. On the other hand, if the two qubits that connect the link have the same value, we represent this with a 1. And then we simply repeat this for every single coupling within this Ising model until we have mapped all of our two-body couplings to single-body fields on qubits. And then once we do this for all of the couplings in our Ising model, we can then distribute them in this nice triangular shape. And then as we've got local fields on our Ising model, we can then do a similar, well, in this case, we can simply map directly local field to local field, and then we place those onto the bottom. So in this case, the spin of the qubit directly matches the spin of the qubit in the LHZ embedding. And so now we're happy, we've got rid of our nice long-range interactions, and everything is local. And yes, we've got our nice Hamiltonian there, which hopefully represents our optimization problem. However, there's one thing that we've now introduced, which is not quite right. So we now have way more qubits than we did in the initial problem. And this means we've got now a much larger Hilbert space. And also the qubits are not connected to each other anymore. So they like to follow their local fields. And this might cause issues. So if I show the exact copy of this diamond shape here, up here, we can see that all of these qubits directly match the couplings in the original Ising model. And all the parities are satisfied in the LHZ embedding. On the other hand, if I were to just flip one of these bits, we have a state here which can be represented in this triangle, but cannot be represented in the original Ising model. And this is something that we want to avoid. So how do we avoid this? We do this by introducing constraint terms, 3 or 4 body constraint terms, which I've represented here with diamonds and triangles. And what this does is this pushes these invalid states, or these states which lie outside what we call the logical code space, pushes them up to higher energy levels, so that the lower energy level spectrum of our problem Hamiltonian directly matches that of our initial problem. Okay, but how does this affect the performance when we use a quantum walk? So what I've now done is I've brought back our plot from earlier, which shows there's a finite time success probability versus this gamma parameter. And this is the results from our initial directly embedded optimization Ising model. And then I've redone this computation instead by embedding using the LHZ. And the first thing to note is that the finite time success probability is a lot reduced. But this is not unexpected because, as I said before, we've introduced a lot more qubits and therefore a larger Hilbert space. So even with our quantum walk, with only one correct solution, it's still harder to find the correct solution in this larger number of qubits. Another thing to note is that this maximum in the success probability has been shifted to the right for a larger value of gamma. This also you might expect because we've introduced these higher energy constraints, and therefore the balance between our initial Hamiltonian and our problem Hamiltonian is shifted. But we would ideally like to do better than this. But there is one thing that we're forgetting, and that we've introduced all these extra qubits. So we now have, we now have added redundancy within our model. So how might we use this in order to improve the performance of our quantum walk? And so the idea is that we can, in order to improve the performance, we can use our decoding method in order to improve the performance. And so as a first example, I've looked at our entire state decoding. So in this case, it's simply the opposite of encoding from our initial directly embedded model onto our LHZ embedding. So you could call this also LHZ disembedding. And if I do a flowchart of what's happening here, though we start off with our initial state, we do our quantum walk, and we end up in a final physical state. This physical state can either be outside or inside the logical code space. If it's outside, then this is when we have these invalid states, which I mentioned earlier. If we want to LHZ disembed, then we can't actually do this. But if we're inside the logical code space, then we can use this disembedding, find a final logical state. This final logical state can be either incorrect or correct, and then we get the results just here. Okay, so, but we want to be a bit cleverer than this, so we introduce another decoding method. So the first decoding method that I looked into was this belief propagation decoding, which is originally introduced in this Priestgill and Co. paper here. And it relies on constraints of 3 qubits, which are different to the constraints, the 4 free-body constraints. And the performance of this, so in this case, once we've done our quantum walk and end up in a final physical state, even if we end up outside the logical code space, we can use this belief propagation decoding in order to find an error syndrome, which then could allow us to find a final logical state, and this final logical state may be hopefully correct. And so how does this perform compared to our entire state decoding? Well, we see already that this decoding method has much improved the performance of our quantum walk. But there's still some room for improvement if we compare it to the directly embedded model. So we next looked at another form of decoding, and this was minimum weight decoding, which was first introduced by this Lidar and Co. paper. And the idea behind this is that if you end up in a physical state, which is outside the logical code space, it minimizes the number of bit flips in order to get back into a logical code space state. And this can also be represented by its own minimization problem. And so how did this perform? We see that this one actually performed very similarly to the belief propagation decoding. And if we look at this flowchart again, we can see that, again, if we end up outside the logical code space, we can use this minimum weight decoding to get an error syndrome, and then use this to hopefully find a final logical state, which might be incorrect or correct. So these are kind of similar, two kind of fairly similar decoding methods, hence why they might perform fairly similar. And so that we still thought there might be room for improvement, so we tried another decoding method. And next thing we tried was spanning tree decoding. And for more info in the context of QAOE, you can see some papers by Anita Weidinger. And so the idea of the spanning trees is that they are defined on the original optimization problem, and they are a subset of the original graph where all the nodes are connected to each other, but no loops are formed. And then if we represent these spanning trees on the LHZ embedding, you can see them here. And in this case, I've used overlapping spanning trees, which means I've allowed qubits to participate in more than one spanning tree. And if we look at the performance of the spanning trees, we see that the spanning trees performs much better at improving the success probability than our other two decoding methods that we used previously. And I'll get on to why this might be the case in a couple of seconds. We also tried another form of the spanning tree decoding, which is non-overlapping, so trying to use our qubit readout a bit more efficiently and not reading qubits more than once. And we find that this performs similarly to the overlapping spanning tree decoder. And yes, so something very specific about these spanning trees is that we read out 3 spanning trees, and we then take the lowest energy of these 3 spanning trees. And this is something to note, because if we take these spanning trees, but instead of picking the lowest energy, we instead use a majority vote to select the correct or final logical state that we want to find, we see that the performance is then reduced back down to similar to the other decoding methods that we used previously. So yes, we wanted to look into why exactly this was happening. And so if we replot our data from the spanning tree decoding, but instead look at the distribution of when there was 3 spanning trees correct, 2 spanning trees correct, or just 1 spanning tree correct, we see that when we have 2 or 3 spanning trees correct, this matches the performance of our spanning tree decoder with majority votes. But this increase in performance that we see here occurs from when we are just having a single spanning tree correct. And therefore, we can only access this if we are doing this lowest energy measuring technique. And so, why exactly might this be such a powerful addition to the spanning tree decoder? So, if we think about the decoding method with the minimum weights and belief propagation and the majority votes, essentially what we're doing is taking this one physical state, and then by decoding, we only have a single choice of logical state that it can go into. So one physical state directly goes to one logical state. On the other hand, with the lowest energy spanning trees, even if we have just one physical state, depending on the energy in your original optimization problem and the value that it gives when you sub in the values, you can end up in 3 possible different logical states. And this in here is where the effect of the decoding method lies. So now we've done this for 5-qubit optimization instances. How does it perform for many instances at different logical sizes? So we then repeated the experiment for the simulations for 4, 5, and 6 logical qubits. And the thing I wanted to compare it against was these reality checks. So these dotted lines I will call the chances. So these are like random chances. So it's kind of like a sanity check. If I just randomly had, so this is K, so this is the number of physical qubits when you encode using the LHZ embedding. If I just randomly found the random chance of finding the correct ground state on this number of qubits. And thankfully, as a sanity check, you can see that even the entire state decoding does slightly better than a random chance, so the quantum walk is actually doing something. However, if you then compare this to the direct chance of the random chance of finding the correct ground state on n number of qubits, it does not perform better than this. However, if we then use our minimum weight or belief propagation decoders, we do find this is improved compared to the random chance. However, so the third thing I looked at was direct chance on k over n. So this represents the direct chance on, so the random chance on the directly embedded number of qubits times k over n copies. So that's the same number of qubits as would be used for the LHZ embedding. And we can see that the belief propagation and minimum weight decoder are outperforming this. But we do find that our spanning tree decoders do outperform this. So this is the first sign that we are doing something really kind of useful with our decoding methods. And the final thing I compared it to, just as a kind of, to see how it was, even though I would say that the directly embedding, the kind of motivation of the embedding is that we wouldn't be able to use the directly embedded models anyway. So I compared it to the performance of a single directly embedded model, and you can see that the spanning trees perform somewhat similarly, but when you then multiply this by k over n copies, they're still performing not as well. But another thing to note is also that in each of these instances, we used a fixed number of spanning trees, so we used 3 spanning trees. And you could argue that as we increase the number of logical qubits, there's an argument to increase the number of spanning trees that we used, and therefore the performance here could potentially scale slightly better than what's shown here. And yes, and with that, I would like to draw my conclusions. For more details, the paper is at this link here. And so, in conclusion, we found that when we are using quantum walks and the LHZ embedding, then we can, by using post-readout error correction methods, we can improve the performance. of the success probability. And we also saw that if we use decoding methods which consider the energies of our states, then this can provide even more improvement compared to the original decoding methods. And possible future directions could be investigation of more or different decoders which could take into account these energies, and perhaps comparison to other decoding methods. And with that, I would like to thank you for listening and any questions.
All right, so we have lots of time for questions. So anyone who wants to ask anything? Testing. Good. All right. Here you go.
Thank you for the talk. I did get a bit lost on the k/n copies
Okay.
comparison. Could you explain that again? Sorry.
So this one, you mean? Yeah, so it's the number of copies which corresponds to the number of qubits in the LHZ. So if we were talking about the 5 logical qubits, then in the LHZ that's 10 logical qubits, I think, yes. And then, no. In my case, it's 15 because I have these. So 15 logical qubits. So then, if you divide this 15 by 5, then you get 3. So it's equivalent to 3 copies of the direct model. So we have 5 qubits. So yeah, 5 times 3 is 15. So this is an equivalent number of copies. It doesn't always correspond to an integer number of copies, but yeah, it's the same number of qubits.
So it would be like k/n many times the probability of the direct chance.
Yes. Yeah.
Any further questions? Okay, Paul. Getting my exercise in. Thanks.
So when you're setting up your LHZ model, you have to put these 4 body terms in with some weight C.
Yes.
And I guess how you choose the value of C critically
Yes.
affects the performance. What do you do in practice when you're trying to optimize your best C?
I set it to a value that, so some of my, I haven't got the link to the paper here, but so this green line here represents a lower bound of this constraint strength, which is actually was actually found analytically in a paper by one of our people in our group, which I can give you the link to the paper if you're interested. I haven't got it here. I'm sorry, I should have added it. But yes, so actually it's kind of an interesting question because weirdly enough, with a quantum walk, there's actually a maxima of this constraint strength below what the lower bound should be. And this it's kind of an interesting question in itself. But actually for the research, because I didn't want if you set it too low, the energy levels from your constraint, your invalid states are going to interfere slightly with the energy levels with the problem that you're trying to solve. So I didn't want this interference to have any effect, so I set it to 2 actually. So yeah, arguably the performance could be better if I'd set it to a lower number, but it's also an interesting question of why exactly we're seeing this maxima here. It's actually because there's this codependence between this calculation of heuristic gamma and optimal and the constraint strength. In that, as you increase the constraint strength, your estimate of optimal gamma is getting worse, and therefore, so this upper line shows if I were to use the optimal gamma, then yes, so the lower bound is happy, so we would be happy setting it at a high value of constraint strength. But if we use this heuristic gamma, actually we see this peak below the lower bound, which is interesting.
But just to follow up quickly, what was I going to ask? Oh yeah, so this analytical lower bound expression is easily calculable for an arbitrary problem graph, or?
Yeah.
Okay, good.
So,
that sounds like an interesting paper.
yeah,
Great.
Yeah,
Thanks.
It's a good paper, yeah.
Thanks.
All right. Does anyone else have more questions while I get the mic? All right. Anyone? I was involved in the work, so it'd be kind of awkward if I ask a question. Anyone? We have plenty of time for any further questions about how this works. I might try to think of something. Yes. So it's captured in this recording.
How specific do you think your results are to quantum walks? Because I mean, the decoding strategies can be applied to many other results.
Yeah. So yeah, I think that's interesting. An interesting question, because I wonder myself whether the effect of there's possibly quite a strong effect from the fact that we are populating excited states in the quantum walk, and whether so we see this improvement by just having this a single correct energy state here. And I wonder whether this would still be the case if you were to use something more like quantum annealing, or something which in theory should populate less excited states, whether the same decoding methods would be as effective, or whether different strategies would be more preferable in those situations. But yeah.
Thanks.
An interesting question, I think.
So I actually am going to ask a follow-on question to that. Have you looked at multi-stage quantum walks with this?
No, I haven't. So that would be definitely an interesting avenue. Yeah.
All right. Any further questions? Yes.
I was wondering what is if you have seen the classical computational overhead of each of the decoding schemes that you have tried.
Sorry, say again?
So how does it scale when you're trying to use the different methods for decoding? How does it scale computationally? What is a computational overhead?
Okay, yes. So there are some things which are more computationally heavy than others. So the belief propagation, because it's a approximation, it's more efficient. So I believe it's like a linear scaling. But the minimum weight decoding, as you could see in the slide, it's in itself a complex problem. So this doesn't scale very well. You'd have to use some kind of approximation eventually. The spanning tree decoding is also an interesting question, because whilst in principle, if you fix the number of spanning trees, this is that's just a fixed scaling. But obviously, as you can see in the final results, the scaling gets worse with increasing size. So you would most probably want to increase the number of spanning trees that you read out. But yes, I've not looked into whether you'd have to, the scaling of this, whether you'd have to increase this linearly, or the number of spanning trees you read out linearly, or more. But yeah, that's where the computational intensity lies there, I would say.
Anyone else? Anyone else have anything they want to ask about this?
So when we are talking about scaling behavior, I wanted to ask how you expect those success probabilities to scale with larger problems. As we see a slight decay here, how do you expect this for like maybe more qubits?
Yeah, so would expect it to continue to decay with the success probability, but the hope is that it would, if we were to use a spanning tree decoding method and increase the number of spanning trees as we go, the hope was that it would decay in line with the directly embedded model, so at least perform similarly as if you were using the direct embedding.
Any further questions? If not, we can just be a bit ahead of schedule. No problem with that. We've already asked quite a lot. All right, so last chance, and if not, we'll the next speaker could come down and we could move on to the next talk. All right, let's thank our speaker again.